Okay, so can we start? Okay, so it's my great pleasure to introduce Professor Gianluca Panati as our first speaker of math colloquia of this year of 2024. Okay, so just as a brief introduction to our speaker, so Professor Panati, he obtained his PhD degree in mathematical physics in CISA in 2002. And then he worked at TU Munich and Roma Sapienza before he became a full professor in Roma Sapienza. So he is an expert in multi-scaling quantum theory and the application of topological and geometrical methods in quantum physics. Okay, so he has also been awarded as the Bessel Prize in 2019. So let's enjoy his talk. The title is "A Mathematician's Look at Topological Insulators." Okay, please.
Thank you very much. I'm very honored to be here for the mathematics colloquium of GSSI. And I'm very grateful to the organizers and to Serena for the kind invitation. I also noticed that there are some PhD students and postdocs who have grown up in Rome. And I think this is very positive, and I hope this scientific collaboration between the two institutions may continue and even increase. So the story I'm going to tell you has something to do with some vague analogy, so to speak, with what happened about 150 years ago in 1869, when Dmitry Igorevich Mendeleev proposed to the scientific community the periodic table of chemical elements. Okay, the very first version of the table, which appears here, was very incomplete and not free from mistakes. For example, you might notice that there is no helium, and the place of helium is taken by lithium. And of course, many elements were not known at that time. But nevertheless, the heuristic value of this table cannot be overestimated. It stimulated decades of research in atomic and molecular physics, first of all in chemistry, and then in atomic and molecular physics. Okay, the periodic table here in its modern version is based on empirical data, so does not rely on any microscopic model of atoms. Nevertheless, it already contains some quantitative information which might suggest the structure of a microscopic model. For example, if you look at the length of the periods, these are 2, 8, 18, and 32. So the length of the period gives some magic numbers, so to speak, which have been later understood by Wolfgang Pauli to be related to the group of rotations. No? For example, you take the irreducible representation of the group of the rotation, which has only unitary representation of integer spin, and its dimension is 12 plus 1. And if you sum the dimension of the representation up to capital L, you will obtain something which multiplied times 2, which has to do with the spin degeneracy, will give. While the table is independent from a microscopic model, it already suggests some features that this microscopic model should have. And as everybody knows, some years after Schrödinger, with the discovery of its equation, he provided the microscopic model of atoms. So here you can read the Schrödinger operator for n electrons in a point nucleus of charge Z times Ze. And this is a linear differential operator which acts on an antisymmetric wave function in n variables, which represent the position of the electrons. And here you can recognize the kinetic energy of the electrons, the interaction of the electrons with the point nucleus, and the electron-electron repulsion in the last term. And as we know, if you fix a Z, the charge of the nucleus equal to n, the number of the electrons, and you solve for the eigenvalue equation, the corresponding eigenpairs, so eigenvalues and eigenfunctions, will provide you the structure of the atom. Okay, and of course, the solution is not possible I mean, there is no analytical solution except for the very basic cases, but you can always solve it numerically, or pretend to solve it numerically. And in this way, every entry in the Mendeleev table has a predictive mathematical model, which of course is not the end of the story, in the sense that a more sophisticated model have been introduced later. For example, you might take into account relativistic correction by considering the Dirac equation for the atom, or you could take into account the structure of the nucleus, okay, which here is a fixed point in the origin, but you might somehow correct by taking into account the nuclear structure. Okay, we jump to 2008, when another Russian scientist, Kitaev, proposed the periodic table of the topological phases of matter. What are the topological phases of matter? I think we are all familiar with the thermodynamical phases of matter. So most of the atomic elements have three phases. We know solid, liquid, and gas or vapor. There are some exceptions. For example, helium has no solid phase, but these are the usual thermodynamic phases of matter. Topological phases are similar, but a bit different. So we are at zero temperature. You're supposed to fix the pressure or the volume, so they don't have to do so much to do with thermodynamic variables. But still, there are different forms of the matter which are labeled by a topological index, which in most of the cases, maybe every case that is still unclear, correspond to a macroscopic observable quantity. For example, the transverse conductivity or the transverse spin conductivity. So let me present you the table. Just I wanted to ask, what is this beep that we hear? Okay, there's been solved. This is the Kitaev periodic table. So let me explain it first of all. So this D corresponds to the dimension of physical space, which goes from 1 to 8. It's very remarkable that there is a periodicity of order 8. So dimension 8 corresponds to dimension 0, dimension 9 to dimension 1, and so on. So it's enough to have dimension from 1 to 8. Of course, physically, we are interested in the first 3 columns. Okay, on the other side of the table, here you classify physical systems according to their fundamental symmetries. What are the fundamental symmetries? Are those appearing in the PCT theorem, which here are labeled in a different way. So first of all, you have the time reversal symmetry, which corresponds to an anti-unitary operator, which might square to plus or minus the identity. Then there is the charge conjugation symmetry, which is still an anti-unitary operator, which might square to plus or minus. Consider the combined symmetry, which, under the assumptions of the PCT theorem, corresponds to parity. Okay, now you do the following. For every system, you put a 0. Now you consider, for example, time reversal symmetry, and you put a 0 if the system does not enjoy time reversal symmetry. If instead the system enjoys time reversal symmetry, then you put a +1 or -1, according to the fact that the square of theta is +1 or -1. Then you repeat the same procedure for the second fundamental symmetry, which is the charge conjugation symmetry. So you have 3 cases for each column. This would be 9 cases, but still there is an additional line, which is the case in which the system does not enjoy time reversal symmetry, does not enjoy charge conjugation symmetry, but it is invariant under the combination of both. Okay, so let me explain this point better. If the system enjoys both symmetries, so both theta and xi, then you have also pi. Okay, pi is without 8 at 0, 1. So if you have 1, 1, then you have 1 also in the third column. And similarly, -1, -1, then you have 1 in the third column. For example, in an Hamiltonian setting, if the Hamiltonian of the system commutes with both theta and xi, should also commute with the product. But it might happen that commutes with the product, but not individually with both the symmetry, and this is the special class A trick. What is happening now? I created some blue lines, or okay. Okay, now Kitaev predicts what happens in these cases. For example, fix the focus on dimension 2, and he's telling you whether in dimension 2 for these symmetry classes you should expect to find topological phases of matter. So there is 0 if you don't expect any topological phase of matter, and if you expect to find it, then there is Z or Z modulo 2, according to the fact that the topological index takes in the integer values or integers modulo 2. Okay, the color emphasizes all those cases in which there have been some experimental counterpart of the Kitaev table. So for example, in dimension 2 and in symmetry class A, so basically with no fundamental symmetry, you find this Z, which correspond to quantum Hall systems and Chern insulators. Okay, this system at 0 temperature are labeled by an integer, which has a geometric interpretation that I will describe later, and physically corresponds up to a universal constant to the value of the transverse conductivity. So the whole conductivity of the system is quantized to an integer. In yellow, you see the Z2 topological insulators. You see that there is an index Z modulo 2, both in dimension 2 and in dimension 3. And this index can also be understood geometrically as the so-called Fu-Kane-Mele index, which has a reinterpretation in terms of geometric abstraction. And all the issues which are here in color, all these correspond to something which has been found in the lab. And of course, there is this big challenge to experimental physics to discover whether also the other entries with Z or Z modulo 2 correspond to something which can be synthesized in the lab. You have a problem with should go here? Okay. Yeah. Okay. Kitaev table have been derived with quite sophisticated methods and which are based on K-theory of spheres. I don't want to enter in that. Let me say that we can regard the Kitaev table as a source of inspiration. Like Mendeleev table, this inspired us to find fundamental microscopic models which exhibit the same topological indices which are predicted by Kitaev. Okay, so the table is model independent, but we are in a sense challenged to produce for each non-trivial entry corresponding model. So I will today focus on class A, which is the best understood class, and I will talk about Chern insulators. These slides is just to emphasize that these systems have been realized in the lab, but only after the theoretical predictions. As you see, the two major papers with experimental realization of Chern insulators, or anomalous Hall effect, as they called it at that time, are 2015, while Kitaev table is 2008. Okay, so in this sense, inspired experimental research in this field. Now, what about models of class A? You can have both discrete or continuum models of the same physics. The most popular, here you have an hexagonal structure, in which you can see the structure is periodic with respect to the Bravais lattice, which is generated by two of the blue vectors, for example, A1 and A2. And also you have these displacement vectors, which allow you to move from a black to a white dot. Okay, now for C being the hexagonal structure, so this set of points in R2, and psi being an L2 function over this hexagonal structure, so a square summable function over this discrete set of points, you can define the translations, which are like the ordinary translation, except for the fact that they take value 0 whenever x minus a is not a point of the hexagonal structure. So sometimes you annihilate the wave function by moving out of the hexagonal structure. Okay, then with the help of this translation, you can write down a discrete Laplacian, which is obtained by summing translation according to the displacement vector and its conjugate, multiplying times so-called hopping amplitude, T1, and then summing over for j from 1 to 3. Okay, then you are taking into account the red vectors, and then you are doing the same with the blue vectors. And here you have a sort of discrete Laplacian, but adapted to the hexagonal structure of the problem, which actually is the so-called tight binding model of graphene. Now, this system has a lot of symmetries. First of all, there is a Z2 symmetry, which corresponds to periodicity. Then a 2 pi over 3 rotational symmetry, which corresponds to the hexagonal structure and to a symmetry of the Hamiltonian. So the Hamiltonian also commutes with this rotation. There is a Z modulo 2 symmetry, which is due to the possible exchange of roles of A and B, of white and black dots. And finally, there is time reversal symmetry, which is an anti-unitary operator, which in this case is given just by complex conjugation. Now, we want to break the last two symmetries while keeping the first two. Okay, the Z modulo 2 symmetry is very easy to break. You create a potential which has the value of +1 on the black dots and +1 on the white dots. Okay, times the parameter m to control how strong is this on-site potential. While you need some time at the table to understand how to break time reversal symmetry without breaking periodicity. So you have to balance things, but I think it's not difficult at the end to realize that a possible choice, not unique, is this one, in which you have the parameter m, which controls the on-site potential, and the parameter phi, which represents physically the sort of magnetic flux, which breaks the time reversal symmetry. So with all these two parameters, okay, this is called the Haldane model. At m phi equals 0, 0 is the tight binding model of graphene. But for phi different from 0, you have broken time reversal symmetry. And so you might have some interesting effects, both in terms of topology and in terms of whole conductivity. Okay, let me very quickly mention that this model is so simple to be completely solvable, which is nice. Okay, so basically you do what is called dimerization. So you can regard your hexagonal structure as let's say Z2 times a set of 2 points, so black and white, right, as a Cartesian product. Then correspondingly, L2 of the hexagonal structure splits are L2 over Z2, the periodicity lattice, times L2 over 2 points, which is just C2. And then you do Fourier transform of these vector valued functions, and you get something which is square integrable over a torus, which physically corresponds to quasi-momentum, so the Brillouin torus, with values in C2. So this C2 is called a pseudo-spin, but has nothing to do with spin. It has to do with the fact that there are 2 atoms per unit cell. Okay, and these slides is just to show you that the model is solvable. So you obtain the Hamiltonian in terms, you decompose the Hamiltonian in terms of trigonometric functions, and you can exhibit eigenvalues and eigenvectors. This is nice, the fact that the model is solvable. However, it's not rich enough to give you the richness of phenomena that can happen in the lab. So in some cases, you might like more complicated models, or you might like models in the, for example, possible continuum model is to have a magnetic Schrödinger operator with periodic electromagnetic potentials. Okay, here you have a Bravais lattice gamma, which is generated by vectors A1, A2, AD. Now, they were the blue vectors in the example before. Okay, this is the periodicity lattice. And now you define your Hamiltonian to be a Schrödinger operator with scalar potential, V gamma, and vector magnetic potential, which are both periodic with respect to gamma. They act on a dense subset, a dense subspace of square integrable function over Rd. And you might also decide to focus on d equal 2 because this is the most relevant case. Okay, in view of the periodicity of the problem, you can decompose the Hamiltonian by using the so-called Bloch-Floquet transform. I prefer a variant of it, which is due to Zach, so the Bloch-Floquet-Zach transform, which is a sort of cosine of the Fourier transform, and is given by this formula. The transformed function depends on two variables. Y should be interpreted as the position inside the unit cell, the periodicity unit cell, while K should be interpreted as quasi-momentum of the problem. You can show that the Hamiltonian in this new representation given by Bloch-Floquet-Zach transform decomposes in terms of the quasi-momentum. Okay, if you are not familiar with this direct integral, it's not important. Just think that you can decompose the problem at every value of the quasi-momentum, and for each value of the quasi-momentum, you have an Hamiltonian, which looks like that. Okay, at first sight, this is even more complicated than the original Hamiltonian because there is an additional K here. But this is not the case because actually this is simpler because it acts on a simpler space. So H of K, the fiber Hamiltonian, acts on a space of functions which are periodic with respect to translations by gamma, with respect to translations by the Bravais lattice. So are locally square integrable and periodic. Okay, this is the reason why I prefer the Zach transform, because otherwise with the classical Bloch-Floquet transform, you will get functions which are quasi-periodic, and this might. Okay, now these are periodic functions, square integrable periodic functions. So effectively are like functions defined on a torus, which is a compact segment. As a result, it turns out that H of K has compact resolvent, so pure point spectrum, which accumulates plus infinity. It is a theorem that these eigenvalues depends continuously on K and even smoothly as far as you are away from the crossing points. and if you move K, okay, you have to imagine that this is a torus. So for example, in my picture, this is a one-dimensional torus. If you move K, then you get these pictures, which are familiar to solid-state physicists. Okay, they are called the Bloch bands. The energy spectrum of the affecting these Bloch bands on the vertical energy axis. Okay, like in the picture here. Now, we ask ourselves, where is the topology hidden in this picture? At the very end, the Kitaev table is written in terms of K-theory, which is a chapter in algebraic topology. So from our microscopic model, we should recover some topological information, some topological index, which is associated to our microscopic Hamiltonian. Where is it then in this picture? So this is what I'm going to show. But first of all, you have to choose a family of Bloch bands, which is locally in momentum isolated from the rest of the spectrum, as the blue bands in the picture here. Notice that I'm not asking, at least for the sake of mathematical generality, I'm not asking that there is an energy gap in the spectrum of the total Hamiltonian, the original Schrödinger operator. It's enough that at every K, there is a gap, and which is uniform in K, which is very easy by continuity and compactness of the torus. Okay, so we have this blue family of bands we are in. And we consider the associated projector, this star, which is written in a different way according to the fact that you are a mathematician or a physicist. In mathematics, we like to write it in terms of the Ritz formula. So you consider at every k the resolvent operator. You integrate it around a positively oriented contour, which intersects the real line only where there is the dashed line here. And okay, and up to this prefactor, you obtain an orthogonal projector, which is called P star of k. If you want to say a different description of it, you can consider UN, which is UN of k is the eigenfunction corresponding to the eigenvalue to the nth eigenvalue. Now, for the moment, suppose it's not degenerate, just for the sake of simpler notation. I mean, it's not essential. You consider UN to be the eigenfunction, and then you take this ket Bragg is the rank 1 projector on this line generated by this eigenfunction, and then you sum over all the eigenvalues which correspond to the blue. Okay, and this is you can prove this is the same object. Then, okay, then now is the boring slide. So this is boring because, well, to prove theorems, you need to assume that the scalar are regularly enough. And so we made a very general assumption that they are so regular as we need. In terms of Kato theory, means that H of k, this is a fiber Hamiltonian, in which you you substitute the real vector k with a complex vector. So this Greek k, this Greek kappa is a vector in CD. And now we ask that this is an entire analytic family in the sense of Kato, the resolvent with compact resolvent. Yes, please. With positive. No, no, it's not assumed that the potentials are positive. No. So it can be whatever. Yes, positive or negative is a matter of regularity. And the rest of the slides, which are not supposed to read in detail, shows you some sufficient conditions which guarantees that assumption 1 is satisfied. So, for example, okay, so assumption 1 is our assumption. But for example, suppose you have a purely periodic magnetic vector potential with fundamental unit cell y. Okay, then a set of assumptions which implies assumption 1 might be, for example, the first blue dot. So in dimension 2, A is essentially bounded. And in dimension 3, A is L4. Divergence of A and V gamma are locally square integrable, both in dimension 2 and 3. So as you see, it's a matter of integrability and regularity, so integrability of the gradient, but no positivity. These assumptions imply that the spectrum is bounded from below. So but, okay. Okay. This is just to say that you have to assume some regularity in order to make the machinery work. And once you have this regularity, you can prove this kind of theorem. So look at the map which sends every quasi-momentum k into the projector P star of k. We can prove that this is a real analytic as a map from RD to bounded operators over the fiber Hilbert space. Remember, the fiber Hilbert space were consisting of functions which are locally square integrable and periodic. So effectively, they are like functions, square integrable function on a torus. And it's tau covariant, which means that if you move from k to k, where lambda is a vector in the reciprocal lattice, so the periodicity lattice in momentum space, then you don't obtain the same projector, but the same projector conjugated with a unitary operator, tau lambda, which is completely explicit. Tau lambda acts on a function of y by multiplication times this exponential of E lambda y. So it's not just a phase, it's a y-dependent phase. So it's a multiplication operator times a phase, and as such, is unitary. Okay, this is a sort of form of periodicity. Then you can take the quotient with respect to this covariance with respect to ZD. And let me skip some details. What you will obtain is a collection of vector spaces parameterized by K in a torus. So when taking the quotient with respect to ZD, basically the quasi-momentum plane becomes a torus, and the covariance, which is a form of periodicity, allows you to glue the spaces at K and K plus lambda in a convenient way. Okay, this is, you are familiar with this language. This is a smooth Hermitian vector bundle given by RD divided the reciprocal lattice, and this is called the Brillouin torus. Okay, now you want to understand what is the structure of this vector bundle, whether it's topologically trivial, so the Cartesian product of the torus times fiber space, which in our case is a finite dimensional vector space, or not. And now we exploit the fact that we are working in dimension 2 and 3, and for dimension small o 1 also than 3, then the Hermitian vector bundles are completely classified by the first Chern class. Okay, this Chern class is actually very computable by the following formulae. For example, if you are in dimension 2, the Chern class, the first Chern class in this case reduces to a number, which is computed in this way. You take your relevant projector as a function of the quasi-momentum K, and you differentiate with respect to K1 and K2. These are operator-valued functions, so you consider the commutator. You multiply times P star of K, and what you get is an operator acting on HF. You take the trace with respect to HF, which exists, and you get a function of K. You integrate it on the two-dimensional, you integrate the corresponding two form on the two-dimensional torus, and then you multiply times this factor. This is called the first, and in this case is the unique Chern number of the vector bundle. And it's a consequence of Chern theorem that is an integer. Why? Because the integrand function actually can be proved to be the curvature of a connection, and the integral of a curvature rescaled by this universal factor provides always an integer, which is independent of the choice of the connection. So it's purely topological. Even if to compute it, you introduce a connection and you compute its curvature, the index is topological. Okay, this is a sort of sophisticated version of Gauss-Bonnet theorem or things like that. Okay, in dimension 3, one has to be more careful because the first Chern class does not correspond to a single number, but to 3 numbers, or if you're familiar with this language, is an element of the 2 cohomology of the 3 torus, but in practice, you have to compute 3 numbers. And what happens? You choose J and L between 1, 2, 3, but different from each other. So for example, 1, 2. You repeat the same procedure as before by taking derivative with respect to Kj and Kl. And you have this integrand function. So you have a 2 form. And now you cannot integrate a 2 form over a 3 torus. So the reasonable thing to do is to consider the 2-dimensional subtori, which are hidden, which are inside your 3-dimensional torus. So if you visualize the 3-dimensional torus as a 3-dimensional cube, you might fix, for example, the third coordinate to be equal to a value, and you have a 2-dimensional torus. Okay, you integrate on this 2-dimensional torus, and the result of the integration is independent of the choice of the subtorus, so of the level set. Makes sense. Okay, and then you get these 3 numbers for the pair 1, 2, 2, 3, and 1, 1, 3. You get these 3 numbers. And the vector bundle is trivial if and only if these 3 numbers are all 0. Another interesting thing that can be proved in great generality is that if whenever you have an orthogonal projector which commutes with the anti-unitary operator, and now, sorry for not saying that, P star without an argument is the collection of all the P star of K at different K. Okay, so you put all them together to obtain a projector in the big Hilbert space. Whenever this commutes with an anti-unitary operator which squares either to +1 or to -1, which is interpreted as a time reversal operator, then the Chern class must be 0, both in dimension 2, 3, and actually this is more general, this is in dimension D. So time reversal symmetric systems cannot be Chern insulators, cannot have a non-trivial Chern index. Okay, so you see in class A, time reversal symmetry is broken. So there is the possibility that we have a non-trivial topological invariant. For example, in dimension 2, this is given by the Chern number, which is an integer, and this corresponds to two-dimensional Chern insulator, so quantum Hall system. If you are in class A1, which are ordinary insulators, then you have a time reversal. The Chern number vanishes. Class A2 are quantum spin-Hall insulators. In this case, also the Chern number must vanish by the theorem before. But it turns out that a time reversal symmetry which square with 2 - 1 equip your Hermitian vector bundle with an additional structure. Okay, it's what we baptize within our work with Domenico Fiorenza and Domenico Monaco. We baptize a time reversal symmetric vector bundle. And then you know that your vector bundle is isomorphic to the trivial vector bundle by a generic isomorphism, so by an isomorphism of vector bundles. And now you can ask yourself whether it's isomorphic to the trivial vector bundle via an isomorphism which preserves this additional structure, which preserves this time reversal symmetric structure. And actually, we computed that there are only 2 cases. So you get an index Z modulo 2, both in dimension 2 and 3. Okay, this analysis gives some. You might have noticed that there is some discrepancy about class A and dimension 3. Because according to the analysis of the microscopic model, which might be the Haldane model, if you want to keep it simple, or a continuum Schrödinger operator, if you want a richer family of models, we should have 3 integers. No? Dimension 3, class A, would be the 3 Chern numbers of the system. While in Kitaev table is 0. So this has to do with a long-standing debate about strong and weak topological indices. So, which I think is a topic which has not been clarified yet from the mathematical viewpoint. So the common idea in physics that is that at some point you should break periodicity. For example, by introducing some disorder, full of disorder, impurities, and other phenomena which breaks periodicity. And the idea of physicists is that when you break periodicity with a little bit of disorder, some of the topological invariants will survive, and they're what's called the strong topological invariants, and other will not. So the expectation, which I repeat has not mathematical justification so far, is that the Chern number in dimension 2 is a strong invariant and will survive, while the 3 Chern numbers in dimension 3, being related to what happens on a submanifold of dimension 1, so not the full 3-dimensional torus, but just a 2-dimensional torus, they will somehow disappear. Okay, but this is still conjecturally as far as mathematics is. But this difference between weak and strong topological invariants open the way to another question. So it would be nice to investigate the difference between ordinary and Chern insulators in position space. So with using periodicity to decompose the system with respect to quasi-moment. As soon as you introduce this order, you break periodicity and you cannot use anymore the block-Floquet transform, the Brillouin torus, and all these structures we use to define Chern numbers. So this was our starting question some years ago. So basically the question is summarized in this table. How to recognize Chern insulators in position space. So there is this dichotomy between an ordinary insulator and a Chern insulator. In this case, assuming periodicity, you have a trivial block bundle, and in this case, a non-trivial block bundle. This has also a physical counterpart. So in the first column, you have a macroscopic observable, which is the whole conductivity, which is vanishing in this column, and is non-vanishing and quantized to an integer in this column. Our question was whether there exists a way to discriminate between the two columns in position space, so without using periodicity. Okay, now comes these results, which presented today the periodic case, but there are also some investigations with partial results in the non-periodic case. Okay, the first fundamental question is which kind of, so we want to understand the relation between the topology of the block bundle and the localization in position space of the electronic state. So the first question is, what is the correct notion of localization we should use to distinguish between the two columns, between the two cases? Okay, there are several notions which are available in the literature. For example, people who work in the community of random Schrödinger operators, they distinguish, I mean, they also talk about localization, the so-called Anderson localization, and they distinguish whether the system is localized or not in terms of the spectral type. So they look at the spectrum of the random Schrödinger operator, which is almost sure, and they consider whether this spectrum is pure point, absolutely continuous, or singular continuous. But for periodic Schrödinger operator, always absolutely continuous. So we couldn't distinguish ordinary and Chern insulators from this viewpoint. Another idea of localization, which also is very popular in another subcommunity, is to look at the projector you are interested in. This was, sorry for the notation, this was P star in the previous slides, and now it's become P mu. And you look at your P star, you can easily prove that under our regularity assumptions, this has an integral kernel which is jointly continuous, so which I call P star of xy. And then one can ask whether this integral kernel has some good decay properties in the modulus of the difference x minus y. And it can be proved by using the so-called Comte-Thomas theory that whenever you have an energy gap in the spectrum of the operator, so this means now a global gap in the energy spectrum, the integral kernel of this projector is always exponentially decreasing with a constant which obviously depends on the size of the gap and will explode close to zero. We use another notion. We look at the localization of composite Vanier functions. I will define them in a while, but just let me anticipate the main idea. So they form these composite Vanier functions. They form an orthonormal basis, which is labeled by gamma in the Bravais lattice and by an additional index A, which goes from 1 to m, when m is the number of relevant block bands, so the blue bands in the picture before. And they are orthonormal, and they span the range of the relevant projector, P star or P mu. Now, notice that, okay, now for the following, I will assume that there is a gap in the energy spectrum. So there is a global gap. Otherwise, I couldn't use from Thomas' theory. So now that I remember, this is the difference between P mu and P star. So P mu means that there is a global gap corresponding to which contains the number mu. Okay, and now it happens that you want to understand the relation between this property of decay of the integral kernel of the projector P mu and the existence of a composite Vanier basis such that the functions in this basis decrease exponentially. And the crucial point is that the first property does not imply the second at all. This maybe is not very intuitive, but it's the case. Okay, vice versa is true, of course, but there is no implication in this direction. And this is clear because the first property follows just from the global gap condition, which is an energetic condition, is a condition on the spectrum of the Schrödinger operator. While the second condition contains some information on the topological triviality or non-triviality of the block bundle. So it's much finer information. Okay, let me introduce our main character, the Vanier functions. So the basic idea is that you look for a compromise between localization in energy and the localization in position space.
Sorry, Gianluca, can you recall me why the W give you some information on the topological triviality?
This will come in the next slides. This was just a sort of trailer.
Okay, sorry.
So to raise the interest for, so the claim is that the W contains information on topological triviality, and now I will try to explain why. Time is
until 4. No, well, we don't have
okay, no rigid time, so. Okay, very good. Okay, the idea of Vanier was to look for a basis which was both localized in energy and localized in position space, as far as this is compatible with uncertainty principle, because of course energy and position operator do not commute. Okay, the idea was the following. You want to fix an energy window, so you consider the projector P star as before, associated to the blue bands. And then for every K, you consider phi1 of K, phi m of K are orthonormal and span the range of P star of K. So for every K, or almost every K, you look for an orthonormal basis on the range of P star of K. At the moment, you don't ask any regularity except the fact that these are square integral. They are associated to an energy window, which is more or less the blue energy window of the slides before. Now, you ask yourself how far they are localized. I mean, you ask, first of all, you notice that they are not, that you can, that this basis is highly not unique. If you have a basis, for example, the one provided by the periodic part of the block functions, you can recalibrate it by a unitary operator. And moreover, you can choose a different unitary operator at every K. So the freedom of recalibration is a map from the dimensional torus to unitary operators of rank M. And this ambiguity is called the block gauge ambiguity. Now, you want to make your Vanier functions as localized as possible. But since the block flow gauge transform to have a Vanier functions, no, perhaps I should introduce. Okay, let me say that you have this block frame. Now you ask yourself whether you can choose this block frame globally smooth. And this might be topologically abstracted, because you can always choose your block frame, which is locally smooth. But maybe if you move around the Brillouin torus, when you come back after one loop, you have a different frame. So in other words, there is competition between regularity, which is a local issue, and periodicity, which is a global issue. And whether the existence of smooth block frames is abstracted or not depends exactly on the topology of the block bundle. And as we mentioned before, this depends, at least in dimensions smaller or equal than 3, this depends only on the first Chern class. So the existence of a smooth block frame is topologically abstracted whenever the first Chern class is different from 0. Now, where is position space? Well, you take your block frame and you do the pre-image of the elements of the block frames via block-Floquet transform, block-Floquet-Zach transform. After a short computation, you will realize that it's exactly this formula here. Okay. And okay, now comes what I was saying before. As the block-Floquet transform is a sort of cousin of the Fourier transform, to have a good localization properties in position space, you should ask to have a smoothness of the block frames over the quasi-moment. And you can be even more quantitative. So for every S, you have that this quantity in position space, this is a sort of expectation value of the position operator to the 2S, corresponds to this Sobolev norm in momentum space. This is the HS Sobolev norm of maps from the d-dimensional Brillouin torus to the fiber Hilbert space. Which is defined the usual way, but just taking the norm in the fiber Hilbert space. Now, suppose that the block bundle is non-trivial, then the existence of a continuous global block frame is topologically abstracted. And then it means that you will not have well-localized Vanier functions in position. However, these results that I said in words is not optimal, because now you might ask yourself, what happens when S is equal to 1? It will exist a system of composite Vanier functions such that the expectation value of x squared is finite or not? Well, S equal to 1 is the Sobolev threshold in dimension 2, but is far from the Sobolev threshold in dimension. I'd expect okay, that in this case, there a priori might exist block frames which have Sobolev regularity HS and correspondingly Vanier functions such that this quantity is finite. But actually, the answer is not. In the topological and non-trivial case, does not exist any system of composite Vanier functions which are one localized, so that make finite the expectation value of the squared position operator. Okay, so we have these two results, and then I think we'll be time to conclude. Okay, first of all, we are always in dimensions smaller or equal than 3 in the previous assumptions. You can always construct a block frame which is HS for S smaller than 1. So this quantity can be always made finite up to a recalibration of the block gauge for S smaller than 1. However, if S is equal 1 or larger, then the existence of S localized block frames corresponds to the topological triviality of the block bundle. And actually, these three statements are equivalent. There exists a composite Vanier basis such that this quantity, so the expectation value of x squared is finite. There exists a possibly different composite Vanier basis, which is exponentially localized, so such that this quantity with an exponential weight is finite. Of course, maybe the basis, this basis is different from this one, but it exists. And the family of projector P star corresponds to a trivial block bundle. So with the help of this, now we have one more line in this synoptic table. So you can see that you can characterize the two columns, time reversals, the trivial block bundle and the non-trivial block bundle, also in terms of some property in position operator. Of course, the challenge is now to generalize this to non-periodic systems. You have to generalize both notions, the one of Chern number, or Chern class, which was based on periodicity, and the notion of Vanier functions, which also was based on periodicity. Okay, this is still a research in progress. There are some preliminary results by the group of Stubbs and Liu in the United States and by the Rome group with Giovanna Marcelli, Massimo Moscolari, Vincenzo Rossi, and myself. Okay. And but still, these are still preliminary results, so I prefer not to mention. Let me skip the proof and go directly to the open problems. Okay, I can stop here, and thank you for your attention.
Thank you so much. So do we have any question or comment from our students? Thank you.
Can you say again what is K-theory thing, how it relates to the
Okay, I can try to
to
explain
the breaking in the
simple words,
periodicity?
but let me say that the explanation will be non-technical in the sense that I simplify a little bit. So when you have vector bundles, it's very natural to classify them up to isomorphism. However, it turns out that for many applications, it's better to consider a weaker equivalence. When basically you say that two vector bundles are K-theoretic equivalent, if there exists, and now I'm simplifying some details, just if there exists a trivial, so let's call X and Y the two vector bundles, they are K-theoretic equivalent. If there exists a trivial vector bundle, such that X direct sum with T is isomorphic to Y direct sum with T. I simplified a bit the true definition. So in a sense, it's a weaker, is a looser classification of vector bundles, which, however, is considered to be interesting from the physical viewpoint because the exact isomorphism of vector bundle is presumably unstable with respect to disorder or other perturbation of the model, while the K-theoretic classification is expected to be robust. This is too long to explain in.
Thank you, Gianluca, for the very nice talk. So I was curious about this notion of strong invariant and weak invariant.
Yep.
I explain better because in my naive knowledge of topological material, let's say, these are all strong in a sense. The phase transition of the materials with these properties are already much more solid with respect to perturbation. If I compare them with usual phases in nature. Sorry, I'm said it very badly. So I mean,
No.
already if you have usual phase transition, these are very delicate with respect to condition.
The problem is that when we say robust or non-robust, we should specify where we're breaking. So if you preserve the periodicity, then all the topological invariants are already robust. So if you vary the model, for example, if you change the parameters in the Haldane model, while preserving periodicity, as the Haldane model does, then the invariant is robust. And actually, I regret that I didn't include in the slides a very nice picture, which certainly you know from Alessandro Giuliani and other people working in this stuff. So we could draw the phase diagram of the Haldane model, which is very simple. So remember that the Haldane model is this Hamiltonian H M phi, which represents, M was the on-site potential. And phi was a sort of magnetic flux. So the role of the magnetic flux is to break time reverse asymmetry. Okay. Now, as a function of m and phi, so I can represent all the models in the Haldane family here. And it happens that there is a line which actually comes from the sinus of something. There is a line like that, and which separates the three topological phases. So what happens is that the model, the Haldane model, is gapped everywhere except on this line, where the two bands, so there are just two bands because it's a two-dimensional fiber. Here on this line, the two bands closes. And everywhere else, the system is gapped, so you can compute the Chern number. And it turns out that the Chern number is +1 here in this island, -1 here, and 0 here. So this is very instructive. You see that you can break. Oh, I'm sorry. I think I exchanged the labels. But okay, doesn't matter because it doesn't matter so much. You can break time reversal symmetry and still having a trivial topological phase. Okay, for example, if you are here, time reversal symmetry is broken. Okay, but still is trivial. And you also see the stability. So if you change the parameters of your model, but you stay here inside, then the invariant of this number doesn't change. No? And the same here. But this is stability at fixed periodicity symmetry. Now we are more ambitious, or let's say physicists ask more ambitious questions. And now we want to understand what happens if you break periodicity symmetry. So you take the Haldane model with a disorder, right? And then in dimension 2, the Chern number is expected to be a strong invariant, so it's expected to survive. But in dimension 3, no. But this has not been done so far at a mathematical level of rigor. These are the theoretical physics papers. I think the conjecture is...
And physically, this corresponds to the fact that...
It corresponds to the fact that in 2 dimensions, the Chern number comes from averaging something on the full Brillouin torus. While in 3 dimensions, the 3 first Chern numbers, they come from averaging on something which is dimension 2 in comparison with dimension 3 of the full torus. So you are just, if you perturb, in a sense, 2-dimensional sets disappears while full dimensional sets are there. But this is very vague. This is very vague, but at least give some intuition.
Thanks a lot.
Sorry if it's a naive question. Around the slide 20, when you were introducing gap with the
20.
Yeah, exactly before.
Okay, yeah.
When you were introducing that, okay, consider a very simple model that our potential is not like harmonic oscillator. I mean, V doesn't go to infinity. Then we will have V goes to 0.
Typically, we are interested in periodic potentials, which might be bounded or might have singularities. For example, Coulombic singularity, but periodic.
Okay. So we may have some pure point spectrum on negative part, I mean, some bounded states. And we do have gap.
If the model is periodic, then it's very rare that you have pure point spectrum because of this picture here. Actually, it's also a theorem, but I think the picture already explains this picture here. So the total spectrum of the Schrödinger operator is obtained by projecting on the vertical axis the bands. And okay, it's a theorem that you will have an eigenvalue if and only if there is a flat band. So a flat band, in a sense, is rare, so you should have an additional symmetry to create a flat band. Actually, okay, now they are very popular for some reason. For example, if you have a Lib lattice, which is a lattice with a particular structure, a particular decomposition, then this symmetry implies that there is a flat block band, and then an eigensymmetries, they are rare, but okay, they might exist, yeah.
So in this case, we do have that the simple gap you introduced, and you just that you introduced two definition of a spectral gap, and the first definition was just simply if there is a distance between two eigenvalues. So on that case,
you refer to this slide here, I guess. So,
yes, before.
so this.
No, before just the previous one.
Yeah.
Yes.
I mean, in this case, if you have
then
if you have an eigenvalue which is not embedded in the absolutely continuous spectrum, so which is out of the absolutely continuous spectrum, then still you have Comte-Thomas theory, and still you have this kind of this should follow from the energy gap with respect to the rest of the spectrum. I think that the really deep case in which you have an eigenvalue embedded in the absolutely continuous spectrum, then this theory doesn't work, and I don't know what the answer is.
Okay. This
in theoretical physics paper, usually one encounters the concept of robust and fragile topology with another meaning. So mine is a linguistic question. The theoretical physics definition of fragile topology or weak topology is that if you add trivial bands to your group of bands, then even if the original group of bands have non-trivial, can exhibit trivial topology just by adding trivial bands. So
it seems to me that this is the physicist reformulation of K-theory equivalent. If you add the trivial bands, it's exactly you take the direct sum with a trivial vector bundle. So
yes, but
so they are reformulating K-theoretic equivalence with a slightly different language, no? But
my question is this connected with the fact, with the definition you gave about fragile topology, meaning that if you break periodicity, then you lose the topological?
No. This is connected with the fact that a good classification should be obtained by K-theoretic classification. So classifying vector bundles by K-theoretic equivalence. Then I think one should produce a microscopic model in which, in the unperturbed case, you have some topological indices, and then you switch on the disorder, and you see whether they survive or not. So whether an observable quantity associated to this topological index, which is still quantized after switching on the disorder. As far as I know, nobody so far answered this question in a mathematically rigorous way. So robustness with respect to disorder, as far as I know, has not been addressed. So yeah, I think there are, as we in the question of Serena, there are different levels of robustness. No, so if you fix periodicity and you work with a family of Haldane models, then this topological invariant is robust, and actually it's also robust with respect to interactions. That is what Giuliani, Porta, and Mastropietro showed in their recent papers. But then if you break periodicity by disorder, then you have a second order robustness, so to speak. So yeah, I think we should agree on which kind of robustness we are talking about.
Okay, thank you.
Yeah, a more a basic question. Like at the start, we introduced the Hamilton, many particle Hamiltonian, like a kinetic part plus the interaction of nucleus electrons and electrons. But then in a quantum model, in a continuum model, we only talk about the one particle Schrödinger operator. So which assumption on the model we had to do in order to reduce from?
Okay, in this talk, I was presenting the theory for one body Schrödinger operator, so one particle Schrödinger operator. You might think that this one particle Schrödinger operator is the result of a mean field approximation. So you start with an n particle Schrödinger operator, you do a mean field scheme, and Serena is an expert of that, and you obtain an effective one particle Hamiltonian if the original model was periodic and if there is no spontaneous breaking of periodicity symmetry, which also might happen in some cases, then the effective one particle model is still periodic. And this would be the continuum Schrödinger operator in my slide. Otherwise, you can also think that you start with one example, the Haldane model in the discrete setting, and you add the interaction. And this is what has been done by Giuliani, Porta, Mastropietro. And they proved that the value of the conductivity, which in the periodic case is proportional to the Chern number up to a universal constant, doesn't change if you have a weak interaction among the parts.
Thank you.
Okay, so if we do not have any more questions, then let's thank the speakers again.